Okay, so just in this section here, all we're looking to do is try to get more familiar with and more comfortable with our function notation. So we're just going to solve a few questions here that we've solved in the past, but we've used our relation notation to help express the question. So for example, the volume of a sphere of radius r is determined by the rule, the function with the rule v of r is equal to 4/3 pi r cubed. That's the volume of my sphere. State the practical domain of the function v and find v of 10. Well, what is a practical domain of a volume? Okay, so obviously we don't get negative values. Okay, the radius, well, you can't have a zero radius. So the practical domain is equal to all the radius values. So what are reasonable radius values? And this is going to be really interesting. A practical domain will be, you're not going to have a zero radius, so we're not going to have zero. Now. There's a few things we could argue. Infinity, okay? Because our radius can be from anywhere from zero indefinite, or can it? For us, is it practical to have a radius bigger than the Earth? Is it practical to have a radius bigger than, as big as a kilometre? So it's a really subjective one, this one. I'm happy to leave it as 0 to infinity because by rights, we can't have a zero radius, so we're going to have positive r values. And there's not necessarily a restriction on our radius. Now to work out v of 10, that's really working out a volume of a cube with a radius of 10. That's just equal to just 4 times pi times r cubed over 3. So what's 10 cubed? 100, 1,000, which is equal to 4,000 pi on 3. Centimetres cubed, we should put units. Actually, we don't have units, do we? So I'm going to put instead, get rid of that. We'll just put, we often write units cubed. Okay? Yeah, because it could be anything. So that's a standard problem. In the past, we might have just said find the volume of a sphere when the radius is 10. Yeah, but instead we now have got, well, the radius, the volume is given by a function, v of r, and find the volume when the radius is 10. All right, what about this one here? We've got a straight line rule, y equals ax plus b, and we've got 2 points that the line goes through. So we could have a quick sketch. So it says that, what this says here, that says at x equal to 1, y equals 7. At x equal to 5, y equals 19. That's what that says. Okay, so if x equal to 1, y is equal to 7. At x equal to 5, we get 19. So if you like, that's roughly, very roughly, our straight line. All right, now we need to find the a and b values. So how do we find the equation of a line? We find our gradient and y-intercept. So we could go through the process and work out a rise over run, but instead we're going to use simultaneous equations. So we know that f of 1 is equal to 7, and that f of 1, if I substitute into the rule, is a times 1 plus b. So therefore f of 1, which is 7, is equal to a plus b. The other one says f of 5 is equal to 19. So that's saying that when x is equal to 5, y is equal to 19. So therefore 19 is equal to a times 5 plus b. So 19 is equal to 5a plus b. Bring the other equation across. So simultaneous, let's subtract them. 19 minus 7 is 12. 5 minus 1 is 4a. B's cancel out. Therefore I get a is equal to 3. If I put a equal to 3, I know that 7 is equal to a plus b. Therefore, 7 equals 3 plus b. B is equal to 4. So if I come over here, therefore, the rule is y is equal to, what's the rule equal to? 3x plus 4. So I probably needed a slightly better axis, so I'm going to cheat. So I'm going to do a horizontal axis about here. And that point there is my y-intercept, which was at the point 0, 4. Find a and b and sketch f of x. That'll do. We could get an x-intercept. X-intercept, put y equal to 0. Put 0 is equal to 3x plus 4. Negative 4 on 3 is equal to x. So that's the point, negative 4 on 3. X. Okay, a familiar problem but with different notation. What's example 11 telling us? Okay, so it says a quadratic function f such that f of 4 equals f of negative 2 equals 0. So what does that statement mean? That means that at x equal to 4, y is equal to 0, which means you have the point 4, 0. At x equals negative 2, y is also equal to 0. So in actual fact, those 2 points are x-intercepts. So if I want to work out a general quadratic rule and I've got the intercepts, I can use a out front of x minus 4, x plus 2, yeah, because they're both intercepts. And I can use this other information. That means that at x equal to 0, y is equal to 16. So if I substitute that in, 16 is equal to a times 0 minus 4, 0 plus 2. Negative 4 times 2 is negative 8. A is equal to negative 2. So to find the function f, so f of x is equal to negative 2 out the front of x minus 4, x plus 2. Okay, so it really is about trying to get used to the terminology that we use, f of x, g of x, those sorts of things. F of 2 equals, means substitute 2 in. Righto. One of the last things we're going to do in this topic is find what we call the inverse function, and it's such an important skill for us. Now, our inverse function only exists, and this is crucial, only exists if our graph or if our function is 1 to 1. Okay, horizontal line crosses once, vertical line crosses once. Now, we can find the rule for an inverse of any function, but whether it exists or not is dependent upon it being 1 to 1. Now, a few key features of an inverse function. To find an inverse function, we actually just swap the x and y values and then rearrange to make y equals again. So just very quickly, if I have something like y equals 3x minus 2, I'd rearrange x and y, just swap them, yeah, and then take the 2 across, and then I could write y is equal to x plus 2 on 3. We don't leave it as y, we say, okay, the inverse function is equal to x plus 2 on 3. So that's physically how we actually find the function. We swap x and y and rearrange, all right? Because we do that, there's a few things that happen as a result of that. So we interchange x and y, we make y the subject, and we give the new function notation f inverse, okay? Now, there's an really interesting feature for any inverse. It means that if I just draw the line y equals x, which is which is just a straight line going through the origin, splitting everything through the middle, 45 degrees. There's my line y equals x. So my inverse function is reflected about that line. Okay, to help us with that graph is the other thing to realise and to remember is we're swapping the x and y values. So if we consider that point there that goes through -2, 1, for the inverse function, it's going to go through the point 1, -2. So 1, -2 may be down there. That there is my y-intercept. Well, it becomes the x-intercept on my inverse function, so it's about here. That point there that finishes only a little bit away from the graph is a little bit away from the graph there. So actually it's we need a bit more of a curve there. So my inverse graph might look a little bit like that, whereas if I was to hold a mirror onto that line, you see a reflection of each other. Okay, so it's probably just a little bit out, but that's roughly what it looks like. What about for the second one? As I said, all the values change. So instead of it going through the point 0, -4, it goes through the point -4, 0. So these 2 points just swap, so it's still there. This one here, instead of going through the point 4, 0, it goes through the point 0, 4, which is up here. Yeah. So this section here, so if you like, I'm going to do colour coding a little bit here on my graph, just to help us identify which sections we're talking about. I'm going to split my sections up into 3 colours. I'll use black on this section here. I'm going to use blue on this section here, and I'll use green on this section here. So let's think about that green section. It reflects about that line. So the starting point was at 4, 0. It now becomes 0, 4. The ending point was at 0, -4. It now ends at -4, 0. And it's a reflection about that line. So that's that section there. This black section here reflects down to there. And this blue section there reflects up to there. So in actual fact, the whole graph, if I just, if I come down here, which I think I was meant to do, yeah, on an axis below, never mind. If I do that whole graph there, I'm just going to go from there to there. That's the reflected graph. Now, the interesting to note here is that this function that we've got, let me rub out the over here. This function that I've got here is not a one-to-one function. So in actual fact, the inverse of this function doesn't exist. But that's okay. We're just practicing the sketching side of it. And I'm going to cheat again a little bit here and draw the reflection. The graph, instead of going through 0, 1, it goes through the point 1, 0, which is here. And instead of it curving up like that, it's going to curve away like that. And what about this line here? Say, if you're not too sure, pick a random point. Maybe that point there might be at -2, +4. Well, then the inverse will go through the point 4, -2, maybe somewhere out there, and it's just a straight line through it. So it might go something like that. A bit longer than the original, but that's okay. So that's what that reflection looks like. So really, don't forget, by reflection, we're saying along that blue line, it's a mirror image. All right. So that's the 3 graphs of our inverse functions might look like. Now, let's have a go at finding an inverse function. So how do we find the inverse? We've got the rule here. So let's just rewrite it by saying y equals the square root of 1 minus x squared. So that's step one. Now we rearrange our x and y values. So we put x equals square root of 1 minus y squared. And now I solve for y. So if I square both sides, I get x squared is equal to 1 minus y squared. Take y squared over and take x squared back. And I get y is equal to plus or minus the square root of 1 minus x squared. How's that? That doesn't happen too often. So that's my inverse is equal to. Now I'm going to leave plus or minus for now, but it's not going to stay like that. Let's have a look at our original graph. I've got an x squared, and as soon as I square both sides, I get an x squared and a y squared. So from this point here, maybe we can see that that's really x squared plus y squared is equal to 1. So if I was to sketch this graph, that's a circle, but let's look at the domain. The domain says we're only sketching the graph between 0 and 1. All right. So if I sketch the graph between 0 and 1, that means these things disappear. All right, actually, so let's leave that part there for now. What else do we know? We've only got the positive square root, which means now I can take away the negative part. So that's actually what my function is. That's the original graph f of x. Keeping in mind what we just did in terms of graphing, I'll use black. Let's put the line y equals x in there. And if I do a reflection, what do I notice? They're both images of each other. So the inverse is actually going to look the same. The graph will be the same, which explains why we get the same rule. The inverse is the same graph. So if we have a look at, it doesn't matter whether I look at the green or the blue, the domain of this graph is 0 to 1. The range of this graph is also 0 to 1. Okay, another key feature is the domain, because I swap the x and the y values, the domain and the range change. So the domain of f inverse is equal to the range of f, and the range of f inverse is equal to the domain of f. So in here, the range of this function here, the range of f inverse is the domain, which means I have to get positive values, which means my actual function has to be the positive square root of 1 minus x squared. That way I get the positive values that I need for here. Okay, so there's my domain and range. I'm going to just bring some of the notes forward a little bit just so you've got access to this information from the next page. So it'll look a little bit different for you on your notes, but that's okay. They're the key bits of information. This function that we sort of need to draw on here. The graph of the inverse function is a reflection of the graph of the original about the line with the equation y equals x. Okay, and I might bring this line into the front page of your notes. So what does that mean? All right, let's have a look at another example here. What have we got? Sketch the graph of 2x plus 5, state the domain and range. I might call that 5 there. It's a positive gradient, and if I find the y x-intercept, 2x plus 5 equal to 0, x equals negative 5 on 2. So that's negative 2.5. So if that's 5, that looks like negative 2.5 there. Might as well get my ruler out. And how's that look? Pretty close. All right, missed just by a fraction, but that's okay. So there's f of x. Got the point 0, 5 and negative 5 on 2, 0. State the domain and range of f of x. Well, the domain and range, may as well stay in black. Domain is R, the range is R. Is f of x 1 to 1? B, yes. Find the inverse function. Okay, so might come over this side. So let's rewrite this function as x equals 2y plus 5. Really what we're saying is we're going to start with the original rule. Swap x and y. Now rearrange. And we get y is equal to x minus 5 on 2. So if I just write as a half x minus 5 on 2. So, and instead of writing a half, because it's not y, we're going to write f inverse of x equals. Find the inverse. Sketch the graph of f inverse on the same set of axes as f of x, state the domain and range. So I may as well I shouldn't have used black. Let's go with blue. So what I know about this graph, it has a y-intercept of negative 5 on 2, which is about there, which is the same as the x-intercept on the other one. If I rearrange this to find the x-intercept, put y equal to 0. So I get 5 on 2 is equal to a half x. If I multiply by 2, I get 5 is equal to x. So I get a x-intercept of 5, which is the reverse of the y-intercept. So we expected that. So now if I draw this graph, if I've got it about lined up correct, there's our 5, 0, 0, negative 5 on 2. So there's our two lines. The domain and range for both the inverse, domain of f inverse is equal to R. The range of f inverse is also equal to R. Right. Key feature, we spoke about the line y equals x. If I draw the line y equals x as accurately as I can here, there's that reflection that we spoke about. And it's no coincidence that they intersect at the line y equals x. All right, so if ever you want to find the point of intersection between the function and the inverse function, it is always on the line y equals x. Okay, which is what this point here is talking about. Okay. Yeah. All right. So key things to note. Inverse function only exists if it's a 1 to 1. Okay. So you can only have a rule. You can reflect all the graphs you want in the world. You can rearrange rules if you want, but the inverse only exists if it's a 1 to 1 function. The domain of the inverse is the range of the original. The range of the inverse is the domain of the original. The graph is a reflection about that line y equals x. All right, which means the point of intersection between the inverse and the function is also on the line y equals x. All right, nearly done. Draw a rough sketch of x minus 1 all squared plus 1 between negative infinity and 1. So first things to note here, turning point. Turning point is at the point 1, 1. And we're going to only sketch half the graph. So the point, where am I going to put 1, 1? What if I put a half? Maybe I can get away with that there. Maybe not. Let's make that 2, 2. So 1, 1 is going to be halfway between everything. Yeah? So the full graph, positive parabola, would be like that. But we're only going to sketch half of it because it's from negative infinity to 1. So I've got that there. And y-intercept 1 plus 1, which is 2, so it needs to be a fraction steeper. So I might as well sketch it properly, hey? Y-intercept 2, so maybe it's a bit more like that. And that's the point 1, 1, solid dot. Okay. And hence find the inverse of the function and state the domain and range of the inverse. Also find the coordinates of the point of intersections of f inverse and f. All right, it doesn't say we have to sketch the inverse, but we might end up doing it anyway. All right, let's find the inverse. So step A, swap x and y. X is equal to y minus 1 all squared plus 1. Subtract 1. Take a square root, which means I get plus or minus the square root of x minus 1. And so I get add 1 is equal to 1 plus or minus the square root of x minus 1. So the inverse function is equal to, now at the moment I'm going to again put that plus or minus because we have to work out whether we want plus or minus. The domain and the range will help me. The domain of f is minus infinity to 1. The range of f is positive 1 to infinity, which means it's the reverse for my inverse function. So the domain of f inverse is equal to the range, which is 1 to infinity, and the range of f inverse is equal to negative infinity to 1. So now let's look at my inverse function that I've got over here. Looking at the range, you need to make a decision. Do I need to have 1 plus root x minus 1 or 1 minus root x minus 1? Now hopefully you're thinking the range is all these negative values, which means I'm going to have 1 and then I'm going to subtract values. So this means then f inverse will equal 1 minus, nearly wrote plus, didn't I? 1 minus the square root of x minus 1 for these domain and range values. So what does that mean? I found the inverse, I've stated the domain and range of the inverse. Also find the coordinates of the points of intersection. Okay, so let's think about that. To find the points of intersection, we've got the two rules equal each other. So your immediate reaction could be, okay, the first function is x minus 1 all squared plus 1. That has to equal the inverse function, which is 1 minus the square root of x minus 1. Who wants to try and solve that? You know what I mean? So it's a bit more complicated, but remembering instead we solve one of them, and in this case I'm going to pick f of x equal to x, because I know that the point of intersection is along the line y equals x. So I reckon you can nearly just about work out where the point of intersection is going to be, can't we? Okay, but let's prove it anyway. So if I solve this, I'm going to expand the left-hand side. X squared minus 2x plus 1 equals x. Bring the x across. X squared minus 3x plus 2 equals 0. Factorise x minus 2, x minus 1. And so therefore x is equal to 2 and 1. Okay, are possible points of intersection. So don't forget that if x is equal to 2, it's the point of intersection with the line y equals x. So my points of intersection are the points 2, 2 or 1, 1. Okay, now look at the graph. They can't both be points of intersection. Okay, because I've only got half the graph. The point of intersection I'm interested in is the point 1, 1. This second point of intersection here is if I had the second part of the graph. Yeah, it's probably not drawn to scale too well. So if I had the section of the parabola that wasn't defined, I'd have a point of intersection at 2, 2. All right. Okay, bit in that. Yeah, have a look at that and see how you go.